Every great detective story starts with a missing piece. In the history of mathematics, few pieces are as famous or as mysterious as the number pi. We know it. We use it every day. But to find its origins, we have to travel back to a time before abstract mathematics even existed, to a place where numbers were a matter of life and death, hunger and abundance. We have a mathematical calculation that is about 3,500 years old. The person who made the calculation doesn't tell us the value of pi. He doesn't use the pi symbol. He doesn't even explain why he uses the method he uses. But when we reconstruct the calculation with modern mathematics, pi emerges, and with an astonishingly close value. So, is this a coincidence? Or was an Egyptian scribe aware of the relationship we call pi today? 3,500 years ago, today, we won't be solving a math problem. We will be doing some mathematical detective work in the dusty pages of history. And our first piece of evidence is a grain silo. In ancient Egypt, grain was not just food. It was a crucial part of the state economy. Taxes, rations, and the administrative system. Therefore, measuring grain was just as important as producing it. And some of the most important people doing the measuring were the scribes. One of the points emphasized in the works of mathematics historian Annette Imhausen becomes important right here. Instead of seeing ancient Egyptian mathematics merely as a primitive version of modern mathematics, it is necessary to evaluate it within the context of scribal practice, education, administration, and daily applications. So, the first rule in our detective work is this: we will not force modern mathematics onto ancient Egypt. First, we will see what they were actually doing. One of the most important pieces of evidence in our file, the Rhind mathematical papyrus, dating back to around 1550 BCE. This papyrus contains mathematical problems and solutions written by the scribe Amos, and now we come across a very important problem for us. A cylindrical grain silo with a diameter of 9 cubits and a height of 10 cubits. But the scribe doesn't start the way we would. The scribe first subtracts 1/9 of the diameter. He subtracts 1 from 9, 8. Then he squares the 8, 64. Then he factors in the height, 640. This is where we encounter the first big question of the file. Why 8? Because the fundamental idea Egyptians used in calculating the area of a circle is this: subtract 1/9 of the circle's diameter, square the remaining value. So, speaking in modern terms, they consider the area of the circle to be approximately 64/81 of the square of the diameter. And this ratio doesn't only appear in the silo problem. In problem 50 of the Rhind papyrus, the area of a round field with a diameter of 9 is calculated. The method is the same again. This means that this operation is not specific to just a grain silo. It is a general procedure used in calculating circular areas. And this is where the detective work gets interesting, because we now have two separate crime scenes: a circle, a cylindrical silo, and the same mathematical trace is found in both. Now let's cross-examine our evidence. If we compare the area calculated by the Egyptians with the modern circle area formula, here is the most famous evidence of the file. The difference is about 0.6%. This is truly quite a good approximation, but here, as detectives, we could make a crucial mistake. From what we've said so far, it is very easy to draw the following conclusion. The Egyptians knew pi as 256 divided by 81, but no, there is no statement in the papyrus that says pi equals 256 divided by 81. In fact, there isn't even a direct statement showing that the Egyptian scribe defined an abstract number pi in the sense we use it today. 256 over 81 only emerges when we re-express the algorithm they used in the language of modern mathematics. So what kind of idea could be behind this method? This is where an important name enters the file: Arnold Buffum Chace. In his comprehensive work and commentary on the Rhind mathematical papyrus, Chace tried to understand the geometric thinking behind these calculations. Consider a possibility. You have a cylinder with a round base. Calculating its area directly is difficult, but comparing it to a square-based object with a similar area is much easier. 1/9 of the diameter is subtracted. 9 drops to 8. Then, 8 squared is 64. Such a geometric comparison could explain the possible reasoning behind the algorithm used. A very important warning at this point. This is not a document showing that the Egyptians actually thought this way. It is a reconstruction, Chace, made by working backward from the calculations we have. So, for the first time in our detective file, we are looking at a suspect, not a piece of evidence. But we have another piece of evidence. Here, the area of the circle is related to the area of the square that encloses it. The result is again 64 divided by 81. This can really look like the trace of pi, but there is a problem here too. Researchers debate exactly how this drawing should be interpreted. For instance, mathematics historian Kurt Vogel is one of the researchers who interprets this shape as an octagon placed inside a square. In this interpretation, the square has an area of 81 units. The area of the octagon comes to approximately 64 units. And this again reminds us of the 64 divided by 81 ratio. But attention, this doesn't lead to the conclusion that the Egyptians knew pi either, because here too, we are making a modern interpretation. Now the question changes. If this method is used to calculate the areas of circles, why is the grain silo at the center of our story? Because round grain silos actually existed in Egypt. For example, large-scale grain storage structures were uncovered in Tel Edfu, round silos, grain storage, administrative structure. Furthermore, 2 models depicting the daily life of ancient Egypt also portray the filling of granaries and the scribes tasked with these operations. Now we have a very nice chain. So, could this method for PI have originated from grain silos? Not yet, because linking archaeological structures with mathematical problems is not as easy as we think. So, what we have is this. The correlation is possible, but causation is not proven. Our main problem is perhaps right here. We sit down 3,500 years later and look at this operation, and we immediately say, this guy was calculating pi, but what was actually in his mind? Maybe there was a geometric intuition. Maybe he was making a practical comparison between a square and a circle. Maybe he was just applying an older scribal tradition exactly as it was. Maybe he never even thought about why the algorithm he was taught worked, and the papyrus we have doesn't tell us which of these is true. And right here, another papyrus teaches us a very important lesson. In problem 10, the area of a sort of basket-shaped geometric object is calculated, but what the object exactly is has long been debated. And there is a very interesting development here. In his 2024 study, George M. Hollenbach re-examined the 10th problem of the Moscow Papyrus. Hollenbach argues that the shape in question here can be interpreted as a circular segment. However, other researchers had previously interpreted the same shape as a hemisphere or a semi-cylinder. The lesson this gives us is very important. Finding the correct calculation in an ancient text doesn't always mean we know what was being calculated. This is the biggest mistake we shouldn't make in this video. An Egyptian scribe uses 64 divided by 81. We see this. With modern mathematics, we say 256 divided by 81. Then we look back from 2026 and say, he knew pi, but history doesn't work that way. But something is missing on the table. A text where an Egyptian scribe says, I calculated the area of the circle this way because I discovered the relationship between the circle and the square. We do not have such an explanation. So what is the verdict? We do not have enough evidence to say that the Egyptians defined pi in the modern sense, but it is absolutely possible to say that the circle area algorithm they used yielded a result that approaches modern pi very closely. And we also know from the papyrus that this method was used in calculating the volume of actual grain silos. Now let's return to the crime scene one last time. With the Egyptian scribes method, when we calculate with modern pi, we get approximately 636.17. The difference is about 0.6%. An algorithm from a scribe 3,500 years ago has come this close to modern mathematics calculation of a circle. Perhaps the real question is not, did the Egyptians know pi? Perhaps the real question is this: do you need to know a mathematical relationship to use it? A scribe can calculate the area of a circle. Without knowing the infinite digits of pi, he can turn a geometric relationship into a practical algorithm without defining it as an abstract constant, and he can get a result accurate enough to calculate a grain silo. So, did we find the trace of pi? Yes. But we couldn't find the culprit because we have the method itself, but there is no document explaining who discovered it, for what purpose, and exactly how. Chace shows us a possibility. Vogel offers us another geometric explanation. Imhausen reminds us that we need to read mathematics within its own scribal and social context. And Bardanova reminds us that although the connection between real silos and mathematical problems tempts us, it is not proof of causation. And Hollenbach's work on the Moscow Papyrus shows us something else. We can still redebate today what an ancient mathematical problem is actually describing. Maybe the Egyptian scribe didn't know pi, or maybe he was using a very good approximation of the relationship we call pi, without having a name for it. Maybe this idea was born in a grain silo, maybe in a field, or maybe it came from an even older tradition of calculation. We don't know this yet, but what we are left with is a small calculation written 3,500 years ago. And sometimes, the greatest mysteries in the history of mathematics are not the questions to which we don't have the answer. They are the questions where we can get very close to the answer, yet never know for sure how that answer was reached. If you are curious not only about the results of mathematics, but also the stories behind them, we have other files here at Limit and Beyond. See you in the next mathematical mystery. If you want to support my vision of building a massive library dedicated to the history of mathematics, make sure to hit that subscribe button. Follow the limit. Go beyond it. Stay with the limit and beyond. Stay with mathematics.